Hi viewers, in this video we are going to discuss the true false based on the rules in numerical computation. I will explain first what is the statement and also explain the justification of the statement. Okay, first explain the statement. What is the statement? First statement is minimize the number of arithmetic operations whenever it is possible. Its justification is this: there are several reasons why it is beneficial to minimize the number of arithmetic operations whenever possible. Efficiency, accuracy, robustness, and memory usage. Overall, minimizing the number of arithmetic operations can lead to the more efficient, accurate, and robustness algorithm with the lower memory requirements. Second statement is avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. If it cannot be avoided, then take the difference before doing other operations. Its explanation is this: taking the difference of two nearly equal numbers can lead to loss of accuracy and numerical stability, especially when dealing with floating point arithmetic. This is because the difference between the two nearly equal numbers can result in a very small number that may be lost due to the limited precision of the floating point. Here is the justification. I will take an example. A is equals to 1.0000 till 1 and b is equals to 1.00 till 2, and we store the subtraction of a minus b in c variable. In this case, the value of c is very small and may be lost due to the limited precision of floating point arithmetic. This can lead to inaccurate results in numerical stability, especially if c is used in subsequent calculation. So overall it is true. Third statement: adding or subtracting numbers, start with the smallest number and work with numbers in ascending order. Explanation is this, or justification is this, like adding or subtracting numbers and starting with the number smallest number and working with the numbers in ascending order can help to improve the accuracy and numerical stability of the calculation. Here we take an example: a is equals to 1.3, b is equal to 0.004, c is equals to 45.67, d is equals to 0.0005. Here we first add b plus d plus a plus c in ascending order. In this case, adding the small numbers first reduces the impact of rounding errors and improves the accuracy of the result. Overall, adding or subtracting numbers starting with the smallest number and working with numbers in ascending order can help to improve the accuracy and numerical stability of the calculation. So, it's true. Now the fourth statement: do not formulate an algorithm which tests whether a floating point number equals to 0. Here is the explanation. It is not recommended to formulate an algorithm that tests whether a floating point number equals 0, because floating point numbers are not exact and their values may be subject to rounding errors. Instead of testing whether a floating point number equals to 0, it is better to use a threshold or tolerance value to check whether the absolute value of the number is sufficiently small. Here is the test algorithm in pseudocode. You can see also. In this algorithm, x is the floating point number being tested and epsilon is the tolerance value. By using an epsilon test, we can handle floating point numbers more accurately and robustly than testing for exact equality to 0. So it is true. By default it is true. The fifth statement is ill conditioning of problem. What is ill conditioning of problem? It is normally due to improper formulation and can be eliminated by a careful reformulation of the problem. A practical way of detecting suspected ill conditioning is to alter the parameters by small amounts and observe their effect on the solution. The justification of the statement is partially true. Ill conditioning of problems can be due to improper formulation, but it can be solved due to the nature of the problem itself. Ill conditioning means that small changes in the input or parameters of the problem can lead to large changes in the output of the solution. So at last, it is true. Therefore, while detecting suspected ill conditioning, broad sensitivity analysis is a useful first step. Addressing ill conditioning may require more thorough analysis and reformulation of the problem. It is true. Next, move on sixth statement. What is sixth statement? After a numerical algorithm is obtained, check if it can lead to numerical stability. In such algorithms, errors grow in each step of calculation. In such case, reformulate the solution procedure to get the stable numerical algorithm. Here is the justification of the statement: as the statement is partially true. Why it is partially true? We can see here. Numerical algorithms can indeed lead to numerical instability, where errors grow in each step of the calculation. This can be due to the variety of factors such as ill-conditioned problems, numerical round-off errors, or instability, as you know earlier. So it is by default it is true. Why it is true? Therefore, while checking for numerical instability is an important step in the development of numerical algorithms, addressing instability may require a more thorough analysis and reformulation of the algorithm to ensure that it is stable and reliable for a range of input values and conditions. Move on to the seventh statement. If severe rounding errors and consequent loss of significant digits is anticipated, and if no alternate formulation to avoid this possible, then carry more significant digits in the critical calculation using floating point numbers in double precision mode. In this mode, the length of the quantity is twice that of the other floating point quantities. Here is the justification of the statement. At last, however, it is important to note that increasing the precision of the calculation can also increase the computational cost and memory requirements of the algorithm. Therefore, it is important to carefully balance the need of precision against the computational resource available and to consider alternative methods or formulations where possible to reduce the impact of rounding errors on the final result. Here it is true. Now move on to the eighth statement, which is double precision requires large memory space and slow down calculations. What is double precision requires large memory space and slow down calculations? Here is the justification. I hope you guys understanding this statement. Here is the justification. This statement is partially true. Double precision requires more memory space than standard single precision, as each double precision floating point numbers require 64 bits, which is 8 bytes of memory compared to 32 bits, which is 4 bytes for a single precision number. However, whether or not double precision slows down calculations depends on the specification context and computational requirements of the algorithm. Ultimately, the choice of precision of a numerical algorithm should be based on careful consideration of the trade-offs between accuracy, computational efficiency, and memory requirements, taking into account the specific context and goals of the problem being solved. So it is true, obviously. Move on the ninth statement. In third iteration of finding square root of 5, we have to find the square root of 5 with starting point 7 using Newton-Raphson method. Relative error is 0.0013. Okay, as you can see that to answer this question we need more information such as formula and the previous approximation obtained. However, based on the given information, we can make a guess only. So we can assume that the formula used to find the square root of 5 is, we can assume the formula x underscore n plus 1 equals to 0.5 into xn plus 5 divided by xn, where xn is the nth approximation and xn plus 1 is the n plus 1th approximation. We can estimate the value of 3 or third iteration as follows. You can see also here. Okay, the final answer we finally obtain solving for x is equals to 3, we get x is equals to 3, x3 is equals to 2.24119. Therefore, the third approximation of the square root of 5 using Newton-Raphson method with a starting point of 7 and relative error of 0.0013, approximately 2.24119. Okay, so it is true basically. Now our last statement is the iterative method are compared on following parameters. The iterative method are compared on the following parameters. What are the parameters? The rate of convergence, the amount of computational effort per iteration, and sensitivity of the methods to starting value and the intermediate values. Yes, it is correct. It's obviously correct because the iterative methods are commonly compared based on the following parameters: rate of convergence, amount of computational effort, sensitivity. I'll provide this PDF in description box. Hope you guys understand whatever I have discussed here. Thank you.